Earlier this year, experts predicted that dark matter may be made of black holes formed during the first second of our universe's existence. Known as primordial black holes, they could be hitting our own planet every 1,000 years, the professor behind the theory has now revealed. The NASA study claimed this interpretation aligns with our knowledge of cosmic infrared and X-ray background glows and may explain the unexpectedly high masses of merging black holes. Asteroid mass black holes, if they were all of the dark matter, might pass through the Earth once a millennium or so, but would be very, very hard to detect. Alexander Kashelinski, an astrophysicist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, told Business Insider. We certainly would notice if one passed near the Earth, since it would affect the orbits of all of our satellites, he wrote in an email. I imagine that it would mess up GPS, for example. However, he claims many black holes of this size would pass between Earth and the Sun once every 100 million years or so. We would, on average, have to wait much longer than the age of the universe for one to pass through the Earth. Though such an event is absurdly unlikely, it would cause some havoc, he wrote. However, he said it could point to a bigger problem. It's possible there is no interaction of dark matter with normal matter, except through gravity, Brandt said. If that's the case, we're in trouble. We've never come to that point where we know something is out there but is completely invisible to our experiments. The team's research predicts all galaxies, including our own, are embedded within a vast sphere of black holes each about 30 times the Sun's mass. In 2005, Kashelinski led a team of astronomers using NASA's Spitzer Space Telescope to explore the background glow of infrared light in one part of the sky. The researchers reported excessive patchiness in the glow and concluded it was likely caused by the aggregate light of the first sources to illuminate the universe more than 13 billion years ago. Follow-up studies confirmed that this cosmic infrared background showed similar unexpected structure in other parts of the sky. About 8 years later, another study looked at how the cosmic X-ray background detected by NASA's Chandra X-ray Observatory compared to the SIB in the same area of the sky. The team found that the first stars emitted mainly optical and ultraviolet light, which today is stretched into the infrared by the expansion of space, so they should not contribute significantly to the CXP. However, the irregular glow of low-energy X-rays in the CXP matched the patchiness of the SIB, and the only other object that is known to sufficiently laminate across this wide an energy range is a black hole. The team concluded that primordial black holes must have been abundant among the earliest stars, making up at least 1 out of every 5 of the sources contributing to the SIB. NASA is currently investigating this issue as part of its Alpha Magnetic Spectrometer and Fermi Gamma Ray Space Telescope missions. These studies are providing increasingly sensitive results, slowly shrinking the box of parameters where dark matter particles can hide, Kashelinski said. The failure to find them has led to renewed interest in studying how well primordial black holes formed in the universe's first fraction of a second, could work as dark matter. Physicists have outlined several ways in which the hot, rapidly expanding universe could produce primordial black holes in the first thousandths of a second after the Big Bang. The older the universe is when these mechanisms take hold, the larger the black holes can be. And because the window for creating them lasts only a tiny fraction of the first second, scientists expect primordial black holes would exhibit a narrow range of masses. On September 14, gravitational waves produced by a pair of merging black holes 1.3 billion light-years away were captured by the Laser Interferometer Gravitational Wave Observatory facilities in Hanford, Washington, and Livingston, Louisiana. This event marked the first-ever detection of gravitational waves as well as the first direct detection of black holes. The signal provided LIGO scientists with information about the masses of the individual black holes, which were 29 and 36 times the Sun's mass, plus or minus about 4 solar masses. These values were both unexpectedly large and surprisingly similar, explained the researchers. Depending on the mechanism at work, primordial black holes could have properties very similar to what LIGO detected, Kashelinski explained. If we assume this is the case, that LIGO caught a merger of black holes formed in the early universe, We can look at the consequences this has on our understanding of how the cosmos ultimately evolved. In the most recent paper, published May 24, 2016, Kashlinsky analyzes what might have happened if dark matter consisted of a population of black holes similar to those detected by LIGO. The black holes distort the distribution of mass in the early universe, adding a small fluctuation that has consequences hundreds of millions of years later, when the first stars begin to form. For much of the universe's first 500 million years, normal matter remained too hot to coalesce into the first stars. Dark matter was unaffected by the high temperature because it primarily interacts through gravity. Aggregating by mutual attraction, dark matter first collapsed into clumps called mini-halos, which provided the gravitational seed enabling normal matter to accumulate. Hot gas collapsed toward the mini-halos, resulting in pockets of gas dense enough to further collapse on their own into the first stars. Kashlinsky shows that if black holes play the part of dark matter, this process occurs more rapidly and easily produces the lumpiness of the SIB detected in Spitzer data even if only a small fraction of mini-halos manage to produce stars. As cosmic gas fell into the mini-halos, their constituent black holes would naturally capture some of it too. Matter falling toward a black hole heats up and ultimately produces X-rays. Together, infrared light from the first stars and X-rays from gas falling into dark matter black holes can account for the observed agreement between the patchiness of the SIB and the CXP. Occasionally, some primordial black holes will pass close enough to be gravitationally captured into binary systems. The black holes in each of these binaries will, over eons, emit gravitational radiation, lose orbital energy and spiral inward, ultimately merging into a larger black hole like the event LIGO observed. Future LIGO observing runs will tell us much more about the universe's population of black holes, and it won't be long before we'll know if the scenario I outline is either supported or ruled out, Kashlinsky said.